Okay, hello everyone. Welcome to the AutoML seminar. So it's my great pleasure to introduce our today's speaker, Jan van Wyn. He's right now an assistant professor at the University of Leiden. He did a postdoc at the University of Freiburg and at in New York, NYU at New York. And yeah, he's going to talk about multi-objective AutoML today. And well, thanks Jan a lot for coming, and stage is yours.
Yes, thanks, Aaron. I'm still sharing my screen, right? Yeah, perfect. So I will be talking today about multi-objective automated machine learning towards accurate and robust neural networks. So in this case, the multi-objectivity comes mostly from robustness is what we will be looking for. And I will, of course, also talk a little bit about this research line next week in Japan, but these are really disjoint topics I'll be talking about. And the work is basically the work is basically based on joint work with two PhD students, Annelot Bosman and Matthias Koenig, who I see here in the room and who coincidentally graduated on this topic last week, and Holger Hoos. And we did this in the context of one of the Horizon projects that we had, the TAILOR project. And since this is the AutoML seminar, I've basically cut out all the introductory slides of, let me first start with introducing Leiden University. So Leiden is this cube town in what we call in the Netherlands de Randstad, basically the agglomeration of Utrecht, Amsterdam, Rotterdam, The Hague. All the big cities are basically clustered around Leiden. So everyone visiting Leiden will have a very good connection to other cities in the area. Leiden is this cute town with these very cool bars. I'm expecting actually Aaron to show this to you at some point very soon. This is our academy building, so everyone who wants to visit Leiden at some point to talk about AutoML related or other stuff, please do shoot me a message, and that would be super cool to meet also in person at some point. And if this does not yet convince you, one of our most famous alumni, I think many of you have seen the movie Oppenheimer. From there, it was also clear that Albert Einstein was for a while not an alumni, but actually one of our visiting professors at Leiden University. So there's actually quite some nice history here in Leiden. And one more piece of shameless advertisement. One nice option to visit Leiden would be the Intelligent Data Analysis Symposium, which will be held in April. This is one of the ranked conferences. Submission deadline is November 21st, and please do spread the word. Please do send your students to this conference, because this is going to be nice. And historically, the AutoML community has actually got quite some nice work accepted at IDA. So please consider sending your students here. And then I've, of course, cut out all of the AutoML introduction slides, because I don't think it would be useful to talk about that today. But some of the projects that we're running here at Leiden University, one of them is using automated machine learning or using learning curves to basically make automated machine learning more efficient with Felix Moore in Colombia, the country, not the neighborhood in New York. One topic that we're very much interested in is meta learning. This is what I often do with my colleagues from Portugal, Pavel Brasdil, Carlos Soares. We're having a project on automated machine learning for large language models. And this is basically as crazy as it sounds. So basically what we are doing here is we're trying out automated machine learning models to optimize the pre-training method of large language, or let me rephrase it, of language models actually. So of course we're not building a random search loop around training ChatGPT, but we are building an AutoML loop around this pre-training type of work. So that's actually some pretty cool work done by my student Andreas Paraskeva. And what we're going to talk about today is mostly robust automated machine learning. And that's, I will tell you, I will give a little bit of background what the machine learning community or the robustness verification community thinks robustness is all about. And I will go into details on that in a second. And then also one more project on automated machine learning for recommender systems in e-health, And one of the books that we published a few years ago, which is available open access, so you can just download that from any place where you find it on the internet. Okay, but let's dive into multi-objective AutoML. And as I said, multi-objectivity, the way that we specialize here at Leiden University is mainly the combination of robustness versus accuracy, or trying to figure out how can we get a good trade-off between those two elements. And basically, what we will look at then, of course, this figure was from our survey paper a few years ago, where AutoML consists out of various components. And basically, what we are in robustness trying to improve upon is this method for a performance evaluation, where basically where we're not just evaluating, let's say, the accuracy in our internal evaluation loop, but we're also going to look at various robustness properties. Sounds easy enough, but it turns out that when you put that kind of stuff together, things actually get a little bit complicated still. And what is robustness? Recently, we actually wrote, I don't see the reference here. This is basically joint work with Jürgen Branke, Heike Trautmann, Holger Hoos, and myself. And we basically wrote a survey on what are the robustness definitions that occur in the literature. And actually, there's a zoo of robustness definitions out there, and the paper is currently under review, so I cannot really yet refer to it, but I think this is already quite nice to see. In the machine learning loop, you often have this real world process that generates some data. From this, often we gather a data set that is now our train set. Based on the train set, we can create we can apply a learning algorithm and create a model that can then be deployed on new instances that are being that can come in from the real world. And at all these three stages, there can be disturbances to the robustness of the model. So at the data gathering phase, you can think of missing values can come in, outliers can be observed. There can be poisoning attacks. All these type of things are a threat to robustness. When it comes to the learning algorithm, there can be things such randomness in the learning algorithm, which it might not be a problem, but it's for sure a disturbance to robustness, right? If the learning model, there might be very obvious ways to deal with it, but it is a way how the robustness is being influenced by deviations of the assumptions of the learning algorithm, and there's of course also coming in disturbances through the different hyperparameters that such an algorithm has. And what we're going to be most interested in today is the disturbances to robustness when it comes to the model deployment. So once the algorithm or the model has been trained, there can be various things how robustness is being compromised when the model is deployed. And then you can think of adversarial noise, random noise, generalization noise, also outliers, and you can think of deviations from the train data. And the thing that I'll be mostly talking about today is making sure that we get networks that are robust against adversarial noise. Because if you're able to obtain that, then typically you get many of the others also, right? Of course, it is still not easy to obtain, but if you are robust against adversarial noise, you're for sure robust also against random noise, and definitely also against deviations from the train data, or at least to a certain extent. The other two are a little bit more complicated. But this is just to say there's many different definitions about what is robustness. We have a certain, let's say, flavor to that, but there's definitely also interconnections. If you're robust against one type of disturbances, you can also be robust against other of these types. Yes, so let's go a little bit into what are these adversarial attacks. I think you've all seen examples of this. We have here an image. No one will dispute with me that this is a stop sign. And now we can, of course, create, or we can, here we have the link, how you can easily verify this yourself. You can create a form of adversarial noise. Currently, you don't, probably you see the difference between those two images, but on the right side, you would still agree with me that this is a stop sign. But this adversarial noise pattern has now been applied to this stop sign, and basically the neural network originally thought, okay, this is a stop sign, it would have agreed with us, but with this adversarial noise pattern on top, it now actually thinks this is a 120 kilometer per hour sign, and that's of course a problem, and we don't want that in our neural networks when we deploy them in the real world. And that's basically what we are going to set off to improve against. I will first also give some background when it comes to what has the general robustness community done against what is the body of literature that they have developed before I will start talking about what we did in this specific space, because I think this background is kind of important, and that flows nicely into the specialization that we have built up here in Leiden. Now, first of all, adversarial attacks. An adversarial attack or an attack basically always has a scope. It is either an attack at inference time, then we call it an adversarial attack. That's the one that we're mostly interested in. But of course, you might have also heard about the other type of attack. That's the poisoning attack. That's not what we're going to talk about today, but you can imagine if there's a survey and somehow there's an adversary that wants to steer the model into a certain area, then he can fill in adversarial data in this survey data, and then the model might or might not be confused by this. But scope, today we're going to talk about the attack at inference level. And typically there's also a form of information that the attacker has at his disposal. And these are all kind of different types of resource areas. You can imagine a black box setting, the setting that basically if you want to attack a deployed model, not always do you have access to the model or to the weights of the model, which could be a realistic setting. But the white box setting is the setting that we are going to be interested in today. You have full access to the model architecture, to the parameters of the model, etc., which sounds like a strong assumption, but also imagine that many of the models that we are using, actually we do to a certain degree have access to these models, right? So imagine if you're driving a Tesla, then somewhere there's a neural network embedded on the chip, and anyone who wants to make an attack to such a model should of course be able to get the weights of that chip. So the white box setting is actually the setting that we probably want to be robust against. And then there's of course also different attack goals. You can have a targeted attack and an untargeted attack. So basically a targeted attack, you basically say, okay, I have this stop sign and I want the model to be confused and to say this is a 120 kilometer per hour sign, which is of course a very dangerous thing to have. The alternative is an untargeted attack. And the untargeted attack just says, I just want the robust, I just want the model to be confused and to make a wrong prediction. And that's, of course, easier to carry out. And we're also going to talk a little bit about the various scopes of such a attack, because you can imagine you cannot be robust against an attack of any scope, right? So basically you have to specify before you set up your experiments. I expect an attacker to have this amount of let's say this amount of freedom, because if the attack gets bigger than this, and I will give an example of this in a second, it's just becoming so obvious that my anomaly detector will take over, and the anomaly detector will just notice something very weird is happening. So the nice part, or the complicated part about the adversarial attacks, is that they're typically imperceivable to the human eye. If you would just look at the right, you clearly see this as a stop sign, but it might there might be some subtle differences. The moment that you start making too big of a distortion, the anomaly detector will take over, and then of course the attack is also a failure. So there's a certain perturbation scope in between. You want to ensure that the model is robust. sorry, I should have said magnitude. So there's a magnitude of perturbation that you want to be robust against. And there's a way also how do you measure this perturbation. And there you can kind of express that in terms of various L norms, for example, the L0, the L2, or the L infinity norm. And one way to visualize this, I think this is quite a nice and easy visualization. On the right-hand side, we see a small model. We see some data points. The model is the line that separates the data points. And of course, here we would be very happy because the model is 100% accurate. But now we, in this case, we define L2 norm as the perturbation measurement, and we define a certain perturbation magnitude, in this case, of let's say maybe 0.05. And then basically what you get is every dot here has a certain circle around it. And basically the attacker, you kind of assume that the attacker has the ability to change the input or to influence the input a little bit in such a way that it if it lands within the circle and you make sure that the classification changes, it is a successful attack. If it lands outside of the circle, you kind of say, okay, the deviation is too big and probably my anomaly detector will pick up on it. And if it doesn't land across the model, then of course the model was robust on this specific instance. So we see here also some examples where the attacker could have successfully confused the model. That's those four items where there was clearly a intersection with the decision boundary. And of course you want to do things about that, and you can also do things about this. I hope that we as the AutoML community are already kind of doing things about this. There's various ways of employing a defense. I think Silva et al. Wrote a very nice survey paper about this. And of course, the simplest thing that you can think of is actually GANs are kind of doing this. You create an adversarial example. You have now found a weakness in your model. You add this adversarial example to your train set, and now you've basically enhanced the train set with a little bit of you've augmented the train set with additional data. And of course, when you train your model again, it will be more robust. This in itself is not a very effective way, but this is kind of the idea behind many of the ideas behind many of the techniques that make a model more robust against these adversarial attacks. And these are basically three things that we should be incorporating in our various training regimes as the AutoML community if we want to be more robust against these type of attacks. But it's still kind of informal. If you've added a certain if you've enhanced the model in its robustness against certain adversarial attacks, you still don't know for sure whether the model is robust. And this is where robustness verification comes in. And robustness verification basically tells you, suppose that I have a certain instance for a certain network, can we formally guarantee that within this attack model, with a certain attack perturbation measurement and a perturbation magnitude, can we formally guarantee that it is not possible to change or to confuse the network on this specific instance. And if you, of course, then are able to verify that for all possible instances, then you have a good impression whether the network is robust against it. And basically the main idea for this is ensure, basically by in a certain way smartly enumerating all inputs close to a given input, that they have exactly the same label as the original instance. And formally that would look like this, and I will go into more detail on the next slide. So here we see X0. It's not super important, by the way. If you don't fully grasp the formals behind this, just think of this as a complicated or a simple formula that can check whether a certain instance is robust. We have here a certain instance X0 that can be one of the dots here in this little data set. Then we want to say for every x that is close to x0, according to what does close mean? Well, that is being mentioned here by the L infinity norm. And as long as the distance is closer than a certain epsilon, we want the prediction of that instance to be the same, or that varied instance to be the same as the prediction that we have on our original instance. And that would look almost a little bit like this. So basically what you then would do, I've drawn here a little inconsistency. It's here the L infinity norm, but L infinity norm would not give us circles. But basically what you then get is for every instance, so think now of one instance, you would basically get this epsilon shape around it, and you would basically try to verify whether every dot in this epsilon shape is on the same side of the decision boundary. Now, and why is this hard? First of all, imagine I've now shown an image consisting I've just shown a model that is trained on two variables, x1 and x2. But keep in mind that when you have image data sets, you're dealing with thousands or millions of dimensions, because every pixel has 3 dimensions already. Now you have maybe an image of 256 by 256 pixels, and you can imagine how complex things then get. And additionally, I've also drawn a linear model, which of course is quite easy to verify. But in reality, of course, all models have all sorts of non-linearities, and the situation gets quite complex if you want to deal with that. And then things get even more complicated when you have certain very diverse network architectures. You of course want to also verify more complicated architectures with all sorts of layer operations, different activation functions, etc. There's various verification approaches and algorithms. Think of MIP, mixed integer-based programming based algorithms, or other types of algorithms. But mostly verifying the robustness of a single instance of a neural network deals with a lot of computational complexity, right? In some cases, you will solve it quite fast. In other cases, it will take. You basically have to go over this entire multi-dimensional epsilon shape around an instance, and that basically is an NP-complete problem, which as the input gets bigger, it will take you more time. Now, that's when I'm going to talk about the work that Matthias performed during his PhD, not just Matthias' work. I will also talk about some other work later. Matthias defended his PhD last week, and basically many of the people that you see on these images, either were involved in the research or evaluated the research. And then today we sent out a little LinkedIn message. And if you have not liked this LinkedIn message yet, please do look it up and like it, because I think that's very warranted in this case. Good. So what did we do? And first, I think it's good to kind of come back to the general typical neural network verification workflow. So this is still a little bit how you can see this neural network robustness verification method. You have a neural network and you have a instance, and that you put into the verification engine. Together you get a verification property, for example, your mixed integer programming property, and then your mixed integer programming engine, and then you get a result after some calculation. Either the property is satisfied. We have found an adversarial example, so no, we are not robust, or the property is unsatisfied. We have not found an adversarial example. So yes, we are robust against this specific image. And then keep in mind, we of course have to do this for all the images in a data set, because we want to grasp a feeling of how robust are we. And basically what that means is that we have to repeat this for many, many instances. And then if you imagine that the running time for an instance can vary between several seconds and several hours, we actually have quite a big compute problem at our hands. And today I will discuss two works that address this problem, or at least that make progress in this work. One is the work of Matthias that he published at AAAI last year, and the other is the work of Annelot Bosman. Actually, I should have updated the year, because as he recently published a JAIR paper about this topic. And those are the two things that I want to talk about in the coming time of my talk. So first of all, verification can get quite expensive, and now we are the neural, let's say we are the neural architecture search community or the AutoML community. So now we don't just want to do this on multiple images, but we also want to do this on multiple candidate models. And that, of course, gives us quite a big grid of robustness properties that we have to verify in those expensive engine calls. And that, of course, is quite expensive. But the good news is we're also the automated machine learning community. So we know about all sorts of methods that can deal with these type of problems. For example, one of the methods is we can do racing. And that means that indeed for some candidate models, we want to evaluate all the instances. But for other models, we only want to, we can already very early on figure out that that we are not as interested in them because it turns out that they are not so robust on those models anyway, and then we can drop them quite early. So basically, the idea is simple enough. We're employing a racing method on these verification problems, and we see if this makes things faster for our purposes. And the goal is, of course, to reduce the number of verification queries while still selecting the most robust model. And one thing that we can use for this, or we cannot use it, that's one of the things that we will try to figure out in this talk. We can maybe already figure out a cheap proxy whether a certain instance will be robust or not. So eventually, what is this all about? You, of course, want to figure out if the decision boundary is far enough away from a certain instance. And that's super expensive to calculate. But one way to figure this out is maybe if the model itself is 100% confident, maybe the model has a confidence or a very low uncertainty in its prediction, then you can kind of assume that you are robust. And if the model is not so confident, then maybe those are the instances that you want to give additional attention to. And this has been formalized as the delta values. And basically the delta value means what is the model output on your most likely prediction minus the model output of your second most likely prediction. And if this is big, then probably you're pretty robust. Of course, this is not a good, this is a proxy, this is not a good assessment. And if this is small, then you might be pretty robust. And this can be used in a racing-based algorithm. So this is actually quite, for no one, this will be a surprise. This is something that you've seen many, many times already in your various automated machine learning projects. We start with a set of all networks. Then we sort the instances in such a way that we start with a certain type of delta values. It says here the highest, but I believe it should be the lowest. I need to double check that, of course. And then verify on each network the instance with that scores best according to these delta values. And then once you have obtained a certain proof that that the network is no longer getting better than the best found network, then we drop those networks and we repeat this loop basically from step 3. And that's the racing algorithm that was proposed in this specific paper. And because there was not a large body of literature yet, there's also no very strong baselines yet. So basically, we want to know how well does this work and how good can you improve across if you would not be using this racing-based algorithm. And I'm saying there's not a lot of work in this field yet. There is a lot of work on robustness verification, but there's only very little work that combines robustness verification with neural architecture search. Yes, and one thing that you can also do, and that's also a trick that, of course, we know from the automated machine learning community. So a statistical test is actually pretty cool, but we can do maybe something a little bit more aggressive. We've seen this also in other papers where we don't wait for the statistical proof to converge on something, But the moment that one of the models lags behind, then already we start we drop it. So then we will drop things even more aggressively. And we can of course look how this works. And that's what we will see on the next slide. So first we see here in blue how the cumulative running time evolves if we just use the exhaustive algorithm, which is of course not a strong baseline, but it's kind of the best that we had at that moment. And we already see that if we employ a racing algorithm, in this case frace, we can very aggressively start dropping networks, and actually we're already order of magnitude faster. And then we can make things even more aggressive when we incorporate this naive racing method, where we even more aggressively drop models, which is represented by the green line. And of course, in no way we are guaranteed to get the best model, right? In this case, we can of course get worse models, but in this specific benchmark, we definitely did get 2 orders of magnitude faster. The best, we were able to select the best network from the set of networks that we were evaluating. And then if we also incorporate this sorting mechanism, so these delta values, then things got even better, because we even earlier were able to identify networks that we wanted to drop. And this is of course one benchmark on the MNIST dataset, but we can also repeat this experiment, let's say, on the CFAR dataset, and there we kind of see a similar trend. So again, exhaustive search, exhaustive evaluation of all the properties on all the networks took most of the time. This can be improved by using the racing mechanism, which makes it an order of magnitude faster. Then again, you can be more aggressive. In this case, you don't get the optimal network. Clearly, being more aggressive does not always give you good performance or the appropriate performance. And then when you incorporate the sorting mechanism, you're not much faster, but in this case, you clearly are more. I don't want to use the term robust because it will overload it so much, but you're clearly more robust than you are getting again the most robust network. So that's actually quite a cool result, because you now get some significant speed ups, but of course significant speed ups compared to this exhaustive evaluation method. And some intermediate conclusions before I start moving to the next work that I quickly want to, I see I have some time left that I want to discuss. So neural network robustness verification is extremely expensive. It's a very cool challenge for us as AutoML community, of course, to work in this space. But we can kind of estimate the likelihood of an instance to be robust by means of these so-called delta values. Those delta values do not really correlate, but they give a good impression, but the correlation turns out to be pretty low with real robustness. But if you then employ it, of course, in such a racing method, you quite often do get, because you only after certain actions drop certain networks, you do eventually get quite often pretty robust networks. And this basically saves us a lot of speed up in runtime. And here on the right is the QR code to this specific AAAI paper that we wrote about it last year. Good, that's one way how the work of automated machine learning, and clearly some advances in automated machine learning can be used to make neural network verification more robust. Let's dive a little bit deeper into what does robust accuracy actually mean. So why are we so interested in those specific epsilon balls, and then what is complicated about those setting those epsilon values or these robustness against certain values properly. And what you might have already wondered, in the previous work, I kind of arbitrarily set, or we arbitrarily set a certain perturbation scope to a certain epsilon. And of course, if you set the epsilon low, there will be many of your data points will be quite robust. If you set the epsilon higher, then on more instances you will find that they are not robust. And one pretty obvious thing that will happen is that your that for a different epsilon value, a different network might actually be more robust. And that's no problem, right? That's just a fact of life, that the answer to which network should I pick, the answer is always it depends. And that's totally fair. But of course, that's something that eventually only the domain specialist can say. I want this specific epsilon, and I want to be the model that's most robust against this specific epsilon. Whereas once you fix it in your experiments, you're kind of stuck to a certain epsilon value. And this is a problem that Annelot started working with. And the thing that she came up with in this work is the so-called critical epsilon, where you're now actually interested in the exact point, or an as accurate point as possible for each instance, that you know for sure for this epsilon value, we are for sure robust. So if we make the epsilon at this value, we are robust. And if you make it bigger, we don't care so much. Of course, we want to know the exact distance to the decision boundary. But we want to set the epsilon in such a way that for this value, we are robust. And basically, then you get on a per instance basis the perturbation scope in which that will not lead to any misclassification. And basically from this, you can quite nicely measure the robustness of neural networks. And what that will look like is, oh yeah, and how do we actually measure this? There are some tools that can obtain you this exact critical epsilon. That's pretty cool, but most of those tools did not really work nicely on a broad set of networks that we tested it on. So one super easy hack how to calculate this is by doing binary search, right? So you first set a high, the epsilon that you do a query, you first set a high perturbation magnitude to your verification engine. If it turns out to be robust, you can increase it. If it turns out to be non-robust, you have to decrease it. You probably have to halve it. And this way, by using a binary search, you can actually nicely find the exact value for epsilon, for which smaller values for sure will be robust. And then basically what you get is, in terms of neural network robustness, a distribution now. And every network now has a distribution or a box plot for which you can express the robustness. And one very nice thing that we have to deal with as a community here is already here shown. Basically, we see here two networks, one ReLU network and one time the MNIST network. And basically, we see here the two lines at which a certain robust accuracy is obtained. Of course, if you have a misclassification, it would be shown here as a robustness of 0, because you basically don't have to change any values in the image to get a misclassification. And one of the very nice things that we will see here is that probably I would go for the right network if I would have to employ a neural architecture search method, or a neural network selection architecture selection method. But it's not entirely clear, right? So this one does have some outliers for which it's absolutely not robust. So clearly this network has some rough edges that you have to deal with, whereas this network is generally less robust. But at least the minimum robustness on the instances that we checked, that's higher. So there is a complicated trade-off that someone has to make at some point. And this gets even better when you look at multiple networks. From this, we have done this experiment, or we have generated those box plots or these robustness distributions on several networks. And there's clearly some network that I would probably not select. This one clearly is not a good decision. But several others will have different trade-offs in what you want to use. And you can actually also plot CDFs, of course, and I won't go too much into detail, but the main point here is that on some instances, one network will be more robust, and maybe also on some parts of the instances, and on other parts of the instances, others will be more robust. So it's also a little bit of a trade-off between what do you really want? Do you want to have your minimum robustness to be at least as high as possible, or do you want on average the network to be pretty robust? Those are two different decisions that you can then make. And now, so of course, the cool build-up that we really want to go towards is, okay, we want to employ this in methods such as AutoPyTorch and AutoKeras, but that's of course quite expensive, and that definitely requires some work that we're currently working on. But we can already use these distributions to figure out several effects, for example, that of adversarial training. So originally I've talked already about several defense mechanisms that you can build in to make your network more robust. And that's something that we can absolutely, something that we can now visually and empirically compare. How good will this work so how good will this adversarial training work, and how much more robust will it make the networks? And that's usually quite hard to measure. But in an experiment that we did, where we had 3 different training regimes, one was a normal training regime, one was employing adversarial training with a certain hyperparameter, and the other was employing adversarial training with the same hyperparameter set to a different value. And here you can already see quite nicely that this adversarial training method significantly, well, I haven't done the test, by the way, but I think I can easily say statistically significantly improved the robustness when this hyperparameter was set correctly. But when you did not set that correctly, then there was definitely an effect because the minimum robustness went up, but generally not something super cool that happened, right? Also, the average kind of stayed the same. So this is quite a nice tool for visualizing these effects and for better understanding what type of things work when you want to make your network more robust, and what things do not work when you want to make your network more robust. So basically the intermediate takeaways before I come with a general roundup is, so robust accuracy itself. The whole community basically measures robust accuracy, and that's fair. But for our goals in neural architecture search, this does not yet capture the complexity of robustness. And these distributions show basically all the nuances that we would need in order to employ this. Of course, there's still the problem. Now we have these nice distributions. How do we select now the neural network? That's absolutely not clear based on these distributions. What do you want? Probably there needs to be a domain scientist in the loop to really make this trade-off. Of course, obvious question is, what about other optimization criteria such as explainability, fairness, etc.? And that nicely ties into some of the works that I think I also want to make you aware of as the AutoML community. So one of the very cool works that Matthias did on this work was he used also hyperparameter optimization to speed up this robustness verification. So the work that I just talked about, basically the work that I just talked about made selecting a robust network from a set of networks faster, but those verification engines can also be made more fast. That's some work that we did with Matthias and that we're currently trying to even further improve. With some master students here in Leiden, there's definitely room for that to use the latest developments in the optimization community. So basically defining even better metrics or defining metrics to even better capture the robustness of neural networks. That's also a very active point of research that we're interested in. Of course, for us, the moonshot would be employ this in AutoKeras or in AutoPyTorch and combine this with some neural architecture search methods to make this more robust. It would be super cool to show some preliminary work on that in AutoML 2026, but fingers crossed. Let's see. And one of the cool things that we wrote a workshop paper about and that we're currently trying to publish in more detail is robustness and fairness combined. So similar to how you can robustify your network by having robustness-aware training methods. and that you can then measure using a robustness distribution. And you can, of course, also make your network more fair by fairness-aware training methods. And then the robustness distributions can actually nicely show you whether then that obtained fairness is also, is that something that you just see in the fairness metric, or is this also something that is now completely, is this also something that is robust and that cannot be altered by smartly changing the inputs of your classifier. And that brings me to one of the ways how I want to round up for today. So adversarial attacks severely limit the safety of neural networks, and robustness verification is one way to solve this. And this basically poses various non-trivial research problems, not just for the Tailor community in the context of where we did this project. This was one of the Horizon projects, but definitely for the AutoML community. I think there's many cool methods from the AutoML community that can be seamlessly combined with those robustness definitions. And then we've talked today about racing algorithms that minimize the number of verification queries and thereby making the search for a robust network faster. We've talked about these critical epsilon distributions to obtain epsilon agnostic assessments of robustness that can then be used in neural architecture search later. And we're, of course, various works on this trustworthiness related problems that we are currently doing in the ADA group at Leiden University. And one important point that I also really want to drive home here. At Leiden University, we now have a pretty strong team on automated machine learning. I've just listed some of the names that people that you might have interacted with at various conferences: Thomas Beck, Mitra Baracci, Holger Hoos, Elena Raponi, Nicky van Stein. And we are actually very able to engage in certain. I've also looked through the work program of Horizon Europe. It's basically, if you control F on robustness, well, it's almost like the whole document lights up in yellow, and it almost feels like there's a lot of things that we can do on this topic together the coming years. And what I would say is, let's look together for opportunities on this. And with that, I would like to round off. Thank you very much.